Hi, Tomusha. Hi, Tomusha.
Hi, Cecilia.
How are you?
Good, how are you?
Fine.
So, I just like last week in a different session, I started like around 6:10. So
Yes.
tonight, I think I start around then? Maybe like 6:10 or 6. I'm not sure exactly when I should start, but
No, it's okay.
yeah, I see six people right now.
¿Qué no me llegó? Yo no escucho nada. No escucho nada. ¿Están hablando o está callado?
No escucho nada, Marta.
Ah,
No, no, va a
No,
empezar,
no.
me parece, en
ok.
minutos.
Me dio la duda si tenía mal el audio o algo, tanto silencio. Hola a todos, perdón.
Okay, so thanks for waiting. I would like to start today's session. So can you all hear me? Does anyone have any problem hearing my voice or? Okay, great. Okay.
Fine.
So thanks, Maria. So I'm Tomoya Sasaki. I'm a PhD candidate at MIT and studying statistics in social science. So I'll be teaching this session until August, I think until the end of this course, I guess, but I'm teaching this session for like next 10 or 11 weeks. And so I'm very excited about this. So I like do statistics for my research, but like my research interest is really about how to apply statistical technique in actual like data in society, or in or like the data related to politics, or the data related to economics. And so uh, I hope like I can provide some actual examples or intuition of how we can apply the techniques we learn in this course to actual real world examples. So let me start today's session. So today we're going to talk about hypothesis testing. And so first, before talking about hypothesis testing itself, I would like to talk about quantile of distribution. Sorry. Sorry. Let's talk about quantile of distribution, which we're gonna use a lot throughout today's session. And then I would like to I will talk about like concepts of hypothesis testing. So what we actually do when we talk about hypothesis testing, and some some concepts that we really need to know. And then we do exercises. I hope you already received my recitation note, but there's some exercises on the note. So I would like to do those exercises on the breakout room. Uh, it- the they are all related to some important concepts in hypothesis testing and actual math of how and derivations. And then if I have some time to work on, I would like to talk about p-values and in detail. So I think I put some figures as appendix on the recitation note, but like I really want to talk about uh, p-values, especially these are very kind of difficult and complicated concepts. So it's really good to know how to apply this in a real world setting and connect the theoretical understanding and a real world example of this concept. So I'm hoping to spend like just 10 or 15 minutes on this quantile thing. And then the concept of hypothesis testing, I hope I can finish in maybe 20, 30 minutes. And for the exercise, I think we need to take a little bit of time. So maybe 30 to 45 minutes on this. And then I hope we have some 30 some minutes to talk about p-values with the figures that I put on the recitation note. So do you have any questions so far about today's logistics? Oh, by the way, if you have any questions, please just post it in the chat or just interrupt me. Like don't like hesitate to like stop me. You are always welcome to stop me at any time. Maybe I might ask you to wait for a bit, but like you can interrupt me. You can just post it on the chat. And also you can like raise hands and using the Zoom function. So in any case, I'll keep like eyes on whatever I can see. So please don't hesitate to ask questions. It's very important to ask questions. This is like one of the only like opportunities that we can interact each other. And it's I think like this is not just a reading textbook or like doing some exercise. It's about like lectures. So I really want your participant, and I hope you can like I might ask questions to you, right? So the interaction is something that I value a lot. So please don't hesitate to ask questions. And I'm gonna talk a lot, and I'm gonna ask questions to you a lot. So yeah. So just to make sure about that. Okay. Okay. So let's start with quantiles. So let's see. Okay. So let's give some definitions before talking about quantiles. So suppose we're talking about some probability distribution, P of zeta, and let's say it's continuous. So it could be, for example, something like normal distribution with mean 0 and variance 1. This is like a typical example of continuous distribution, right? And let's say we are generating random variables from this distribution. And let's also define, let's see, this is too bold actually. And let's define a value alpha, which lies between 0 and 1. Do you have any questions so far about the setting that we're talking about right now? Are we all good? Okay.
Yeah.
Yeah. Okay. Great. Thanks. Thank you. So this is like the basic setting we're talking about. So then let's define the quantile. So definition. So we say one minus alpha quantile of, sorry, this is bad writing, quantile of this distribution P for value Y such that probability of random variable X, it's smaller than Y, is equal to 1 minus alpha. So this is just a definition. We're not talking about anything like fancy. We're just talking about definition so far. And we define this as small Q of alpha. This is just like I write down the definition and no more than that. So, and this might, but this definition is a little bit, maybe some a little bit hard to like, you know, kind of get intuition out of it. So I'll, in a second, I'll just like give some, I'll just draw something here and to like kind of provide some intuition. And, but do you have any questions so far for this definition? Like, it's just definition, but like, you know, I just want to make sure that this concept is not okay. Are we all good? Okay. Okay. So this is like, you know, too abstract. And so, you know, I would like to give some concrete example. So example. So let's say, okay, we're going back to our previous example and continuous and normal distribution. It's a continuous distribution, and let's say the distribution we're talking about has mean 0 and variance 1. And let's say alpha is equal to 0.05. Like this is just random setup that I'm just using for like just sake of explanation. So what does it mean when we say quantile alpha? So it means that when we're drawing, sorry, this is bad, not great writing, but normal distribution with their mean 0 and 1, we're going to look at let's use different color. Blue works. Let's see, red. That might be better. Okay, so it means that we're gonna look at the area that has 1 minus alpha, right? This corresponds to this part. So 1 minus alpha is the space, like, so we define alpha is 0.05, so this is 0.95 in this example. So this area is 0.95, and when we say quantile, it's the value here. This is the quantile of a distribution. Quantile of this distribution. And actually, this is nearly equal to. Do you know what this value is? Like nearly equals. Does someone know this? What this quantile alpha, quantile 0.5 is, 0.05 is, sorry.
$6.5.
So no, sorry, could you repeat that again?
6448 is 1.64.
Yeah. 1 point, sorry.
6448.
Yeah, exactly. Yeah, 1 point. Yeah, let's say it's 1.6. Yeah, 5 for now. But yes, exactly. Yes. Thanks, Matteo. Is that correct pronunciation? Matteo?
That's correct.
Okay, thanks. Okay, thanks. Yes, thanks for answering. Yes, so this is quantile of this quantile 0.05 of the normal distribution. That's 0.05. That's 1.65. So this is the one example of a quantile, and I think this is. I hope this is a very kind. Just give you some intuition about what quantile is, and so like actually, so this lecture defines quantile like this, but some textbook or maybe other people might define quantile in a different way. So this is not related to the lecture, but like some people call this value like a z value, for example. Like, so there is some slight difference in how people express this quantity, but like in this lecture we define this is the quantile. Okay, so we're not talking about this because it's an out of scope of this lecture, but like there's a different way to define this quantity, but like this quantity we say it's quantile in this course. Do you have any questions for this example? Can I go ahead? Okay, so
yeah.
Okay, thanks. Yeah, thanks for responding. Yes, thanks. So I would like to do a little bit of examples, and for this I want your participation. So I would like to give a distribution and alpha. So please give me the quantile of it. So it's not going to be a difficult one. I hope it's like a simple one, but yeah, please think about this. So first, let's stick with our current example, normal distribution with mean 0, variance 1. And let's say our alpha is 0.5. Then what do you think this quantile is? Quantile alpha. Can
0.
someone give me
0.
0? Yes, yes, exactly. Could you elaborate why it's 0? Yes, it's exactly 0. Yes.
Because if you look at the graph, it's
Yeah.
right in the middle, and the
Yeah.
mean of the normal distribution is 0.
Yes, exactly. Yes, thank you. Sorry,
Marta.
I couldn't find. Okay, thanks, Marta. Thanks. Yes, yes, exactly. So we are looking at the. We need to look at the center of the distribution to find the area. Sorry. It's actually 1 minus alpha. So sorry, I'm moving around a bit, but 1 minus alpha equals 0.5. Yes, exactly. Thank you. Yes, thanks. Yes. Okay. Yeah, great. And then I would like to do a little bit more, maybe trickier one. Then what about this one?
Infinity.
Infinity, which infinity?
Plus.
Plus? So when we're talking about alpha is equal to, yes, this is like a tricky part of the definition we have actually, but
Because
no.
it's a closed interval, it's an open interval.
Yeah, it's 1 minus alpha, right? So we're looking at
minus
0 part. Yes, so it's minus. Yes. But like your idea is correct. Yeah, this is the part that I really want to emphasize. That the definition is a little bit tricky, but yes. So yes. So we're looking at the point that's gonna have a distribution 1 minus alpha equals 0. But then, this is a continuous random variable, so you need to go all the way to the tail of the distribution. So you need to find the point. So you cannot find until you reach a negative infinity to find the point that has 1 minus alpha equals 0. Okay, so let me see. Okay, let's see this. Maybe we can do this as an example as well. So this is another example that we need to use when we're talking about hypothesis testing. So I really wanted to elaborate this, but let's again talk about normal distribution with mean 0 and variance 1. And now we want to find so this is normal 0, 1, 1. So now let's say we want to find these two areas. So these two areas to have 1 minus alpha equals 0.05. These two plus area. So maybe let's not use 1 minus alpha. Let's say each of these places have 2 over minus 1 minus alpha equals 0.05, which means 1 minus alpha is still 0.05. Sorry, this is a little bit messy. I'm going to below. So we're doing a little, so we want to find the two tails of distributions to be 0.025 each. Then sorry, let's not use alpha actually. I think this is a little bit. Let's see. Let's use other notation for now. Sorry, let's use other notation for now. What then if so we're still looking at the tail of this distribution, and what is the alpha value that's going to come here when we want to look at this value? Actually, this is like almost the answer, but like this value to become the tail of these two distributions, this distribution. What is the alpha we are looking at?
196.
Sorry, could you say that again?
196.
196. Yes, 196. Yes, exactly. 196. And it's, yes, so it's gonna be 0. Yes, exactly. Sorry, I always messed up, but yes, exactly. This is 2 of 0.975, and it's 196. Wait. No. Sorry, I messed up. It should be, it's correct, 0.025. Sorry. I also messed up, but like this, sorry, this, yes, exactly. This is 1.96. And which means that this part should have this distribution 0.025, which means that other area, let's use different colors. This area should have 0.975, including this tail. But like, if we do this way, we're gonna have these two tails add up to 0.05, because each tail has the probability mass of 0.025. So we're gonna use this tail, like how the tail is distributed, a lot when we're doing hypothesis testing. So I just want to review this for to make sure that we're on the same stage. So do you have any questions for these examples that we've just covered?
No.
No, thank you, Matteo. Yes, okay, great. Okay, so let's go to our next step, hypothesis testing. Okay, so I'm gonna first provide like informal kind of explanation or informal definition, informal version first, and then we would provide more formal explanation and definition of this. So as usual, let's define the model and the experiment, the statistical model and the statistical experiment. So the statistical model we're going to use is Bernoulli. So can someone remind me the sample space of Bernoulli?
Zero, 1.
Yes, 0, 1. Yes, thank you. 0 and 1. Yes. And can someone tell me the parameter space? Where this parameter of Bernoulli should be located?
0, 1.
Yes, it's between 0 and 1. Yes, including 0 and 1. Yes. So this is a model, and with the statistical experiment, we have is random variables, x1 to xn. It's, let's say it's IID from some true parameter p theta, p star. So this is the experiment we have. So you might feel this is redundant, but like defining statistical model and statistical experiment is a very, very important when we're when we're doing parametric model, which is a core concept of this course. So I'll try to like provide this definition about it. So again, we're doing this for hypothesis testing. So giving these two components of statistical two components, we like do hypothesis testing, something like this. For example, does the data support the hypothesis? The P of star is 1/2. So for example, you want to know whether, so for example, if you're doing coin flip, you want to know whether the coin is biased or not. Maybe if you're like a data scientist at the company, then, or pharmacy, or like, and you might like, test the effectiveness of medicine. And you want to know whether the medicine actually had a positive effect on the patient or not. And you have a like 0, 1 data. So if it's 0, like the patient doesn't improve, but if it's 1, you like the patient they kind of recovered thanks to the medicine. And then you have like the probability P, which is the probability that the medicine actually works for the patient. And that kind of scenario is like a typical hypothesis testing. We're going to talk more about examples later, but like this is kind of one example that of hypothesis testing in real world. And what's the test going to tell you? What does it tell you? Is, so for example, it's going to provide kind of like sort of yes or no, but with some quantification. So this is an important part, the quantification of uncertainty. So it's going to provide yes or no. So it's hypothesis testing. So you're going to get whether your hypothesis is like a true or not, given the data you have. But it's not about that. It's going to give you some uncertainty estimate. How uncertain your hypothesis testing is. That's another quantity that you're going to get when you're doing hypothesis testing, and it's very, very important, right? Because like it's almost impossible to say something for 100%. So you need to have some uncertainty quantification, and that's what hypothesis testing, statistical hypothesis testing, is going to give you. So do you have any questions so far for this informal version of explanation? Okay, let's go to the formal. Sorry, does anyone have a question? No? Okay. Okay, great. Okay, so sorry. So let's go to the formal version of definition, or more formal explanation of hypothesis testing. A formal explanation of hypothesis testing. Okay. So we're gonna use the same example here. So let's copy this Paste. So we're still in the world of Bernoulli, and we want to do some hypothesis testing with this example. So when we're doing hypothesis testing, we're gonna set up two hypotheses. Can someone elaborate one of those two? The first one is like no hypothesis, right? Which we often denote with H naught. And can someone give us the another one?
Alternative
Yeah,
hypothesis.
alternative. Yes, thanks, Matteo. Yes, alternative. Yes. And we call it H. We usually call it H1. So this is like a kind of component we're talking of hypothesis testing. And when we actually do tests, so when we actually conduct tests, what we actually do is we define the test statistics, which is function of the data, and which usually which should be either 0 or 1. Oops. And what does it mean if it's 0 or 1? It says, can someone remind me what happens if size 1? In the lecture?
You reject the null hypothesis.
Yes, exactly. Yes, exactly. Thank you. Yes, you reject null hypothesis 0, H naught, which is equivalent to say the data does not support H naught. So this is a subtle difference here. Sorry, does anyone have questions? Okay. So we're not saying the data support alternative hypothesis H1. We're just saying the null hypothesis, the data does not support null hypothesis. So this is a very subtle difference, but like we really want to make sure that this is not saying that the data support the H1 alternative hypothesis. What the data can tell is whether to reject the null hypothesis or not. And it's so I think in the lecture we say that these null hypothesis and alternative hypothesis are asymmetric. And this is a part of the reason why we call these two hypotheses are asymmetric. Okay, so then what does it mean when we say psi is equal to 0? It's just the opposite of this. So I'll just write it down. It's not going to reject null hypothesis. So which means that the data
rejects
is the data aligns with H naught. So the data is consistent with H naught, right? So this is what the kind of conceptually, formally what we're going to do in hypothesis testing. So do you have any questions so far until now? Like, so we kind of formally define what hypothesis testing is, and we just talk about what they mean in the actual like a real world example a little bit. And so yeah, do you have any questions so far and for this until now? If not, okay, yeah, if not, I'm gonna go ahead and talk about a little more detail of this. So there are a couple components that I would like to talk about related to this hypothesis testing. So one is simple versus composite hypothesis. Can anyone tell me what they are? Can anyone try? What's simple then? Can anyone help me explain what simple hypothesis is? According to the lecture? All right, so simple hypothesis is something like H naught P stars is let's move it here. So it's example like something like P stars 1/2, for example. So this is like a one example of simple hypothesis. And when we say it's simple, what it actually means is that like some hypothesis has only one value, basically. Take only one value, theta naught, in the entire possible like value that you want to test for hypothesis testing. So this is like what it means when we say we're talking about simple hypothesis. Then what's a composite hypothesis?
It's when we're looking for a condition to be met, like theta less than or greater than.
Yes, that's a good example. Yes, great, thank you. So like the example we had in the previous page was P star is not equal to 1/2. So it's that there's a multiple possible values of theta. So this is not theta. Sorry, let's remove close theta. And the sample and the possible values of the test statistics, or possible values of the hypothesis that you want to test. So this is simple versus composite, which is the first concept that I want to talk about. I think it's pretty straightforward. Like if it's simple, like you're just only testing whether something takes particular value or not. If you're not talking about simple, you're as Mark just mentioned, you're talking about some like condition which like P is greater than 1/2, or P is not equal to 1/2. which potentiality can take multiple values. Okay, so let's next go to another, I think, is a very important concept, which is two-sided versus one-sided. Let's give an example again. So can someone give me an example of two-sided hypothesis testing? So when we say we have H naught is P stars equal to 1/2 from previous example, two-sided hypothesis is P star is not equal to 1/2. This is a typical example of two-sided test. And the reason why we call this two-sided is partly because we're rejecting the possibility that P star, we're trying to reject the possibility that P star is greater, large enough, far large enough from 1/2, and P star is small, far enough from P 1/2. So we're trying to disprove two, like we're trying to disprove one thing, but in kind of a way, we're trying to disprove two different things at the same time, because we don't want P star to be closer from the bottom and closer from the top of. Sorry, does anyone have a question? Okay, yeah, sorry, if I don't catch any question, please, your question, please just repeat, like, or type it in the chat. I might, like, you know, especially when I'm talking, I may not be able to catch your question, but like, yeah, please, if that's the case, please repeat it. So let's talk about one-sided. So if we say H naught is, let's say, yeah, could you, let's stick to our Bernoulli example, and could you give me an example of one-sided hypothesis testing? Anyone?
If you want to prove that it's
Yeah.
the alternative is greater than 1/2, for example.
Great. Yes, yes, yes. And yeah, you can say, let's say maybe it's smaller or maybe you can still not equal to, right? Yeah, it's greater. Yeah, let's do this. Great. Yes, that's great example. That's a great example. So when we're talking about one-sided hypothesis testing, we're just looking at the one side of the value of P, and we're not saying we want to disprove that P is like, you know, so we're not looking at the other side of the possibility that P star is close enough from the bottom. We're just saying that, okay, P star should be greater, but like we're not interested in whether P star is closer from the bottom of the potential values of P. So what I would like to do now is so actually, like a side note, two-sided hypothesis testing is usually better, as for the reasons that I'm going to explain later. But there are some cases one-sided hypothesis testing might make sense. So I just want to ask you, when can you use one-sided hypothesis testing? Does anyone have any idea when we can safely use one-sided hypothesis testing instead of two-sided? No?
When it
Does
doesn't
anyone
make
have any
sense to
idea?
look at the other side.
Yeah, so yeah, could you give us actual like real world example of this?
For instance, if you can only have positive numbers, for instance, real numbers, in positive numbers, I mean.
Yeah, sure. Yeah, that's, yeah. I think like maybe my, like
For
real
example,
world- yeah.
when you are trying to test one drug, for example,
Yeah,
and you want to know if the success is greater to some number, you don't care, or if it's greater, you just want to prove that is that you have to discard that is lower than that number. Any number above that is okay for you, or
yeah, sure. Yeah. Actually, yeah, that's a great example. Thank you. And I want to rephrase a little bit. Maybe I might rephrase too much, but like the medicine example is actually what I had in my mind. So yeah, let's do this example. So medicine test. So recall that when we're doing one-sided test, you're only testing whether P star is greater than 1/2, right? So let's say, okay, so having that in mind, let's think of a medicine test. So you are a data scientist, and your company fielded a medical experiment with a new medicine. And now, so let's assume that the previous medicine had a probability of 1/2 success. So it's going to cure the patient for probability 1/2. And you have a new medicine, let's say new cheaper medicine. And you want to know the probability that this new medicine gonna cure your patient, right? So this is a new medicine, then the probability of the patients get recovered is unknown. So you want to know what's the probability that this new medicine is gonna recover the patients who take this new medicine. And what's important here is that the medicine your company has created does not assume that this new medicine does not need to be more effective than the previous medicine. But what you want to know is whether this cheaper medicine, the cheaper new medicine, is less effective than the previous medicine or not, right? So you don't care whether this new medicine is better than the previous one, but you only want to know whether this new medicine is as good as the previous one. Then this is like a typical example of one-sided testing, one-sided test. So sorry, let's say this is P star, but because what you want to know is what you want to disprove is that this P is not smaller than 1/2, right? So what you want to know is this new medicine is at least as good as the previous one. And if it's better than the previous one, that's fine. But like you don't care about that. If it's new medicine, you just want to know whether this is as good as the previous one. Then this is a typical example of one-sided testing. so your now alternative hypothesis is it's greater than 1/2, but like it doesn't tell whether it's far greater than 1/2. It just tests whether it's greater or equal than 1/2. So this is like a typical example one-sided test. And I really want to talk about this because one-sided test is sometimes useful, but in many cases it's not used. It's not a great idea. But like to give the situation that one-sided test might work, I want you to convince that the one-sided test could be useful only in the particular scenario. So if you want to know whether this new cheaper medicine is better than the previous medicine, you need to do another hypothesis testing, which is two-sided test. Okay, so we just talked. I think I just talked.
Sorry, Tomoya.
Sorry, yeah, go ahead.
I didn't understand this one because you said that the new medicine should be better than not.
Yeah. So yeah, sorry. So what? Yeah. Sorry. Go ahead. Yeah.
No, I was saying that this new medicine should be better than the previous one.
No. So sorry. Maybe I might phrase it a little bit. My phrasing was a little bit confusing, but like you as a data scientist wants to know whether this new medicine is at least as good as the previous one.
Okay, and shouldn't be
one.
greater
sorry,
than.
Yeah, sorry, could you?
Shouldn't be.
Yeah.
Shouldn't be p greater than 1/2?
So it's you want it to be greater or equal than 1/2, right?
Yes.
But you don't care how better it is, or you don't care like the degree of betterness. You just care whether it's at least as good as the previous one, or so you don't want you don't want the new cheaper medicine to be worse than the previous medicine. That's like the scenario. That's the scenario.
Exactly.
The way you said it in the end,
Perfect.
it's the precise definition you gave us earlier. You're just rejecting the hypothesis that the new medicine is worse than the previous one. You're not saying it's better. You're saying it's not worse.
Yeah, exactly. Yes. It's not better. We're not saying it's better. We're just saying it's not worse than the previous one. Yes, thank you. Yes, thanks for rephrasing. Yes. Yeah, let's clarify that. Yeah, thank you for the question. Yes, thanks.
Un poco sutil para mí, pero bueno.
So it's not worse. It's a little bit weird phrasing, but not worse than the previous one.
And how would you write it if you want to prove it's better than the other?
Yeah, so if you want to prove that's actually better than the other, I think you need to do two-sided test in this particular example, because like if you're doing the one-sided test is just so this as in this example, like you cannot you cannot reject the possibility that the new medicine is like equally good as the previous one, and you really want to do the two-sided test, which has H naught is not equal to 1, and you really H naught is, so this is like the actual test you want to do. and you also want to have, so actually I'm going to talk this a little more detail later, but like there's a little bit different test that you need to have for
Okay.
yeah. But thanks for asking. This is a very, very important part, I think, of the hypothesis testing conceptually. So I just want to cover this. So, okay, so let's go to the exercise that I hope you already received that. And I also want to share the Google form. I think you already done this in the past few weeks, but I will. Okay, yeah, I'm gonna share it over the chat as well. But so if you don't have the recitation note, I'm gonna share it over Zoom right now. So just take a look at it. Oops. And so I'm gonna create a break. Oops. Okay, so I'm gonna create a breakout room now. So let's do like 10-15 minutes for this one, and after that come back to this main room and talk about each question one by one. Okay, so I'm gonna walk through your breakout room, but so if you have any questions, please feel free to ask. So let's create 2 breakout rooms today. And okay, so yeah, please start discussing. Go to the breakout room and just start discussing. Mm.
Recording in
Okay.
Not sure everyone is back, so someone's still missing. Never mind. Okay, it seems everyone is back. Okay, so sorry, I think there are a little bit confusion what we're gonna do, but I think we can go. I think we can go one by one for this exercise, and maybe I might not being able to talk about the appendix figures we have, but I'll hope I can briefly go over it when I have time. So let's explain this exercise 1. So we're still in the Bernoulli world. So exercise in 1. So, but for now, we only have 4 random variables. IID, and as usual, we have a sample space of 0 and 1 with parameter P belongs to somewhere between 0 and 1 as well. So this is like a simple our setting, and we are given the hypothesis. P stars. So these are both simple hypotheses. And so we would like to do some tests based on for these different hypotheses. Okay, so our test statistics is whether there are 3 or more heads or not. So this is like the exam setup we have. So as usual, if we're gonna reject the hypothesis, is if psi is 1 and not if psi is 0. Okay, so this is a setup. So do you have any questions for this setup we have?
No.
Are we all good with this example? Oh, sorry.
No.
No, okay, great. Okay. So then let's go ahead and let's see. Okay, let's talk about 1A first. So write out all elements in the rejection region for the test psi. So this is what we're being asked. So we would like to know the element of the possible like combination random variables that would reject this given hypothesis H naught, which is the the possible combination of random variables, that's gonna be psi is equal to 1. So this is asking possible combination of xi's, where I is equal to 1, 2, 3, 4, such that psi is equal to 1. So this is basically what this question is asking. So we would like to know under what condition psi is equal to 1, basically, in other words. So as usual, psi is function of x's. And here, psi is function of x1, x2, x3, and x4, right? And this is like, this condition is by definition. And from the setup, we know that this is true. So psi is equal to 1. Oops, why? Oh, let's see. Sorry. Oh. Psi is equal to 1 when there are 3 or more heads among x1, x2, x3, and x4. So this is what we're asking. So let's go direct. So I'm gonna provide one example of this. So, or can someone try what these values should be? Sorry. So let's see. Can someone give me one example of this? X1 is X2, X3, X4. What kind
all
of
heads.
Sorry?
All heads.
All
Heads.
All heads, yes, exactly, yes. If we have all heads, yes. Thank you. That's exactly right. This is one example. And actually there are 4 more. Can you give me one more? Can someone give me one more?
First 3 are 1 and the last is 0.
Okay, yeah. Exactly. And for other examples, I'm not gonna write down everything, but like you can do x3 is equal to 0. You can do x2 is equal to 0, and you can do x1 equal to 0. And all of these 5 combinations can satisfy the condition that psi, condition of psi, which is whether there are more than 3 heads or not. So this is basically the answer. These 5 combinations are the answer to this question.
I have a question.
Yeah, go ahead, please.
So here you have only 2 options. Either P is 0.5 or
What?
P is 0.9.
Yeah.
Those are your. So you will assume that in the case that, for example, only one coin is head, you are in the 0.5 distribution. That's or you accept 0.5 is right.
Yes.
But that's because there are not other possibilities, because you only have 0.9 and 0.5.
Yeah, exactly.
0.25 is not an option, for example.
Yes, exactly. Yes. So for this particular question, your totally right. So we're not examining any other possibility other than P star is equal to 0.5 or 0.9.
Okay.
Yeah, so this is a very weird setting. I totally understand this is a very weird setting, but this is like I just want to provide some like extra grounded example with a more simpler setting. So this is a weird setting, but this is very simple setup. So yeah, so thanks for the question. It's a very good point. Yes, this
Thank
is
you.
a very weird, but like we kind of reject H naught, and like the alternative hypothesis is also simple hypothesis. So it's really weird setup, and your question is totally legitimate and totally understandable. So but thanks for asking. And yeah, so that's a great point. Yeah. So this is a very, you're exactly right. Okay, so let's do 1B. So here we're asking to rewrite the event used to define psi. So these are, we have 5 events in total. And we want to rewrite in these in terms of xi. So this is like also a little bit tricky. Maybe the rephrasing of the question was a little bit tricky, but let's go back to our definition. So heads is greater than 3, then we're gonna say psi is equal to 1. And if not, we'll say psi is equal to 0. So this is maybe you might it might be hard to a little bit like grasp what we're asking, but we're basically saying to mathematically define there are 3 or heads greater or equal than 3. So this is like, we want to define this quantity mathematically. And to do so, I think for the sake of time, I'm gonna do this by myself, but this gonna work, right? So this xi, x1, x2, x3, x4, and we define heads as 1. So if we add up x1 to x4, we should have those sum greater or equal than 3. If we observe more than 3 heads, if we observe greater or heads greater or equal than 3. So this is what we're asking. So, and how we define this quantity. And we can actually rewrite this in terms of sample mean by simply saying, so we're gonna multiply both sides with quarter. And then we're gonna get sample mean and the left hand side. And we're given the 3/4 on the right hand side of this inequality. So this is what we're asking for this question B. So it might be a little bit tricky, but I hope you kind of. Oh, sorry. Go ahead. Sorry, I couldn't catch. I saw someone was asking question. No? Okay. Let's go to 1C. So we're asking, what is the probability that psi is equal to 1 when H naught is true? So maybe this is all very complicated. Maybe the wording itself might confuse you, but like this, because that's kind of a nature of hypothesis testing. So, and I'm gonna here, I hope I can like provide some, with this example, I can provide some like a very important part of a hypothesis testing. And actually the question that I had in the breakout room was exactly on the point of what I want to tell from this question. So we're asking the probability that size equal to 1 when H naught is true. And I want you to rewrite this term in a different way. So when we say H naught is true, under this setup, it means that we're gonna assume that P star is equal to 1/2. Basically, this is like what this H naught is true implies. So we're asking, what is the probability that size equal to 1 when we assume that P star is equal to 1/2? And this is exactly what hypothesis testing is doing. And I'm gonna show you, I'm gonna explain in a minute. But here, basically what you need to do is compute the probability that so this is a quantity that you want to know. So you want to know the quantity of this quantity. Oh, sorry. Which is a probability that xi, sum of xi's are greater than or equal to 3 when P star is 1/2. And this is I'm not going to go into the details of math, but like this is just computing the probability under binomial distribution with probability 1/2. So what you want to compute is this quantity and this quantity. So sum of these two quantities. So this is a situation where 3 heads, and this is a situation where we got 4 heads, right? We're just going back to the definition of binomial distribution. And this is gonna give you approximately, not approximately, actually 5/16 is probability you're gonna get from this this computation. So this is like kind of a this is like a very, very important when you understand the hypothesis testing, because hypothesis testing is all about the distribution under the situation where no hypothesis is true. So it's all about null hypothesis. So you set up null hypothesis, and you have the data in your hand, and you calculate some test statistics. And what you're going to do is, okay, so let's assume that this null hypothesis is true, and we can generate some distribution. And then what's the probability that we're going to observe the data that we have in our hand under the situation where null hypothesis is true? So in this situation, what we're doing is that we observe some particular data, and then let's assume that P star is equal to 1/2, which is a null hypothesis. Then what is the probability that we're going to observe this data under the assumption that P star is equal to 1/2? And this is like how you do hypothesis testing. This is a procedure. So it's all about the distribution under the null hypothesis. And I really want you to keep this in your mind when you're doing this, because it is a very, very important concept. So I don't want to rush, but I need to do a little bit. I want to go a little bit quick here. So I'm not gonna go to the in detail for this question, but the question D is basically asking when P star is equal to 0.9. So what is the probability that we're gonna observe 3 or greater heads when P stars is equal to 0.9? And if you do this computation, you do very similar binomial again, and you get approximately 0.95, which you got exactly correct based on this Google form. So this is great. So actually, so 1C and 1D is actually a very similar thing, but like so 1D is like you're computing something under this H1, but like usually you only compute this kind of quantity under the null. So this is like this 1D is just for practice. And let's do 1E. So this is also a little bit tricky question. So suppose that psi is equal to 1, right? Which means the data you observe, your data already tell you this, right? Your data already tell you that x1, that x1s you have, it's gonna add up to 3 or greater. And this is what this question is telling you, right? And then we're gonna ask, what is the probability that P star is 0.9 under H0? So this is a really, really tricky again, but so this it might be very, very tricky question actually, given the question I got in the breakout room. But when I say H0 is true, it means we're gonna assume P star is 1/2, right? So when we say under H0 is that we are the scenario where we assume P star is equal to 1/2. So
0.
Yes, exactly. So this quantity is equal to 0. Yeah, exactly. So this is a little bit tricky question, but like the reason why I put in this question is that I really want to emphasize that hypothesis testing is all about assuming the null distribution is true. Under the null, what happens? It's all about under the null, what happens. So under the null, it's P star is equal to 1/2 in the situation. The probability that P star is 0.9 is 0 because we're assuming that P star is equal to 1/2. under the null. So actually this is like really tricky question, but like I hope this example is giving you some intuition and some important component of hypothesis testing. Okay, so does anyone have any question about this exercise so far? Okay, then I want to move on to the figures that I've created. It takes me a while to create this. I really want to explain these figures, but I only have 5 minutes, so I'm gonna be very quick. So what I want to tell here is again, so what we're doing when we're doing hypothesis testing. So we're in the scenario where alpha is equal to 0.05, which means that if we're gonna look at the quantile. So actually this is quantile 0.05 over 2, right? And this is where, so again, we're doing is we're have a distribution based on no hypothesis. So again, what I want to emphasize here is that this test statistics comes from data, right? We're going to compute some test statistics from the data. This is what we learned in the lecture. And so any hypothesis testing, we're going to compute test statistics from data. And then we assume that suppose the null hypothesis is true. So in this case, we're assuming that, so some like there's, okay, let's say this is normal. We have some null hypothesis, like we're not going to give concrete example here, but and based on the null hypothesis, how unlikely we observe this test statistics. This is what hypothesis testing is doing. And when we say, okay, so we're gonna observe test statistics at like this that probability given the null hypothesis, that is a p-value. The p-value is a random variable actually, but this is also the probability you observe, or sorry, you obtain the test statistics under the assumption that null is true. So this is a p-value. So this is a definition of p-value. So this is a random variable because it depends on data, right? So this is function of test statistics, which is also the function of data. So I really want to emphasize here that this is all p-value test and the null hypothesis, p-value and test hypothesis testing is all about null distribution and how unlikely you observe this test statistics under the null. That is a p-value. And that's why p-value depends on data and p-value is random variable, but it's a probability as well. So this is like a kind of a really the concept that I really want to emphasize here. And I have some other examples for one-sided tests and two-sided tests without rejection, but like I'm gonna skip here for the sake of time. And finally, because I'm doing statistics in social science, I really want to talk about p-hatting, which some of you already hear about. But so so in this particular case, so I'm saying I'm assuming that the data is generated from Bernoulli from 0.55. So I'm creating random variables, IID random variables, and I'm testing whether this value P is not equal to 0.5. So I'm pretending that I don't know the true value of this distribution, and I'm just testing whether it's gonna be equal to 0.5 or not. This is like the exercise I'm doing here. So test statistics. So I actually it was already written in the lecture notes. I'm not going to go into the detail, but because it's n is equal to 100, we're going to have 100 here, and we're going to compute xn. So thanks to central limit theorem, we know that this is true. And I'm just computing test statistics based on this equation and generate p-values from, assuming that this is true. So what this distribution is showing is that under the assumption that this distribution is true, what is the probability that the data you have gonna generate the test statistics that you can create from this equation? And if you do like n equals 100, like and you generate you do this exercise 10,000 times, and like approximately like 80%, 90% of the time, you're gonna correctly reject the hypothesis with alpha equals 0.5. This is what this figure is showing. And if you increase the number of n, actually you are more likely to reject the hypothesis, because like it's actually more than 9,000 times you're gonna so I'm doing the same exercise, just changing this value n. And you're gonna, so which means that if you have more and more observation, you're more likely to get smaller p-values. Even the true distribution behind the data is the same. But this has a negative down effect as well. So this example here, I'm assuming that the true distribution, the true distribution that generate data is 0.5, a parameter 0.5, and I'm testing whether this p is not equal to 0.5 as a null hypothesis. And then what you're gonna get here is that you actually mistakenly reject your null hypothesis for almost 5 to 10% of your times. This is what we call p-hacking, because which means that when you have a multiple iteration of same test or similar test, you happen to get the p-value which is smaller than 0.05. And this is like example of p-hacking. And I'm sorry that I didn't have enough time to cover this, but like if you have any questions, I'll be around for a couple more minutes after from now. And you can ask me maybe next week as well. But like this is like, I just wanted to like show why when and how p-hacking happens with this example. So I'm gonna stop the recording here and today's session. So thanks for coming. I'm sorry that I rushed a little bit at the end, but I hope this session was useful for your for the homework next week.
Thank you,
so
Maya.
much.
Bye.
Yeah.
Thank you.